Welcome. The purpose of this video is to review Hess's law, which we went over in class, but we were a little rushed at the end of class. So here's another resource to review this type of problem. So this is one way to determine delta H or enthalpy change for a reaction when you cannot do it experimentally, when it is theoretical. All right, so Hess's law, the big thing that we learn with Hess's law is that reactions can kind of take multiple forms. We generally think of reactions making products. For an example reaction we've seen a million times now is something like HCl plus NaOH making NaCl and water. So we think of our reactants just changing into products. We know, even just from something like organic chemistry mechanisms, that the bonds breaking in the reactants cannot always immediately reform to new bonds forming in products. Sometimes, instead of going immediately from these molecules to these molecules, you need to go through an intermediate. Sometimes you go from reactants to an intermediate, and then intermediates to products. What we learn in Hess's law is that you can add the enthalpies going from reactants to intermediates, intermediates to products. You can add up those enthalpies, and that will be the same as the enthalpy from just the reactants or products. So there's two ways to solve problems like this. Let's take a look at both ways. Here's an example of this type of problem. This is our direct route. Carbon plus 2 hydrogen plus 1/2 O2. Like I mentioned in class, sometimes there's half coefficients. I know it looks weird, but sometimes in energetics we do write half coefficients. You'll see that in redox reactions too. We kind of violate our own rules here to make the math a little bit nicer. And then we have two intermediates. My job is to take a look at the intermediates and see how they fit up to my overall reaction. What do I mean by that? Well, I see that I have these reactants make CO2 and H2O. All right, so that means that CO2 and H2O, those molecules are not in my overall reaction here. That means that they have to be intermediates. All right, so I have reactants to products, C plus 2H2 plus half O2 to these products. The delta H there is negative 878 kilojoules per mole. Great. I now see that CH3, OH yields CO2H2O. So I can draw my arrow from my reactants to products and put my enthalpy change. All right. But now I go back and I take a look at Hess's law and I see that in order for this to be true, I need to move from reactants to intermediates, from intermediates to products. Right now, I'm moving from reactants to intermediates, then from products to intermediates. Well, it turns out that all reactions, all chemical reactions, are theoretically reversible. All reactions are reversible. And if a reaction in the forward direction is exothermic, in the reverse direction, that same reaction with those products becoming reactants will have the same change in energy, but will be, excuse me, I think I said that incorrectly. Let me say that again. If going from reactants to products is endothermic as a positive delta H, then going from the original products to the reactants will be exothermic, and vice versa. So I can reverse any reaction. I can reverse any reaction, and all that happens is that the sign of my enthalpy changes. All right, so now I can just apply Hess's law to get this delta H. I'm going to take negative 878 kilojoules per mole and add 676 kilojoules per mole. All right, if drawing out that diagram looks a little weird to you, there's another way to set this up. It's going to be the same exact math, but it's just kind of an easier way to look at it, at least for me. Some people prefer the diagram. I prefer seeing it algebraically. You do the same math, so it doesn't really matter. Okay, so now I'm going to write my intermediate, C plus 2H2 plus 1/2 O2 yields CO2 plus 2H2O. Great. So I've written this intermediate. The goal of writing my intermediates is I'm trying to find a way for, and I'm actually going to erase this so we can see this completely. I'm trying to find a way for these equations to add up to give me this equation. Okay, so I see that I have these reactants on the left. That's what I'm ultimately going to need, so that looks great. Here, well, I see that the CH3OH, that's what I'm going to need in my final equation, but it's in the wrong place. So I see I'm going to have to switch that reaction. CH3OH, and I'm going to put CO2 plus 2H2O. Now, when I switch my reaction, what do I need to do? I need to change the sign of the enthalpy. 676 kilojoules per mole. Delta H, negative 878 kilojoules per mole. Let's see if I've done it. I'm going to write out the complete equation I have. So I'm going to add up everything here. C plus 2H2 plus 1/2 O2 plus CO2 plus 2H2O. Yields, I'm going to add up everything over here. CO2 plus 2H2O plus CH3OH. Awesome, awesome, awesome. Now I see I have CO2 in the reactant, CO2 in the products, those cancel. In class, I just canceled it right up here, but to be the most correct, you can write out the complete equation and then cancel. I also have 2H2O, 2H2O, and those cancel, so what's left over is C plus 2H2 plus 1/2 O2 yields CH3OH. And that is what I wanted. And so in order to find the enthalpy, I just need to add my enthalpies that I've come up with here, which are negative 878 and 676 kilojoules per mole. Same math as above, just a little bit different of a way to look at it. All right, hope that helps. I'm here to answer questions. Have a good day.